Hello and welcome to this tutorial on raster analysis. In this tutorial, we're going to talk about what raster data is, what is raster analysis, and what types of raster analysis are supported by iDesktop. So let's get started. So raster data is basically image data in the simplest terms, and it is the basic data for GIS applications. And in iDesktop, raster analysis is the analysis based on raster dataset, and these are the different types of raster analysis that are supported, such as surface, vector, building DAM, raster statistics, etc. And under surface analysis, we have extract isolines, extract given isolines, slope analysis, view shed, 2-point visibility, surface distance, surface area, etc. So we will take a look at some of these one by one. So this is the overview of this tutorial. We're going to talk about raster data types, and we're going to talk about how to interpolate to raster, which is IDW, kriging and spline. And finally, we will talk about surface analysis, which includes isolines or isoregions, slope or aspect, orthographic image and hillshade, surface area and distance, and finally, identification of value. So let's see how raster data compares with other types. Now there's real-world data that has points, lines, and regions. In vector data, points, lines, and regions look something like this, where points are actual points and lines are actual lines and regions are actual region polygons. But in raster data, the structure is based on pixels. So as you can see, the points are made up of single pixels, the lines are made up of lines on multiple pixels, while the regions are made up of full shapes of pixels. So there are three types of raster datasets. The first is DEM models, which contain pixel values that represent elevation information. Then we have grid data, which is pixel values that represent business information such as temperature, rainfall, etc. And then we have image data, which is remote sensing images, satellite images, aerial photos, or other photos. So basically, different types of images. So the DEM dataset and grid dataset are the main datasets that are used for grid analysis. Only several grid analysis functions can be used for image datasets, such as resampling. So what we're trying to say here is that DEM and grid datasets support most types of raster analysis, while image datasets are limited when it comes to analysis functions. Now let's talk about interpolation. What is interpolation? Interpolation is a process of predicting or estimating values at unmeasured points using sample points with known values. Interpolation within an extent is to estimate data for unsampled points using known data at measured points within the same region. So what is the purpose of interpolation? The purpose is to get a raster dataset based on a point dataset. We estimate the cell value using interpolation method and get the correlations between point values. The interpolate field type should be numeric. Now, an application example of interpolation to raster is when we want to get rainfall isolines based on the collected rainfall data in some observation points. Now, Supermap provides three interpolation methods for modeling or creating a surface. They are inverse distance weighted interpolation, or IDW, kriging, and RBF or spline interpolation. The method that we select usually depends on the distribution of our sample data and the type of the surface that we want to generate. Now, no matter which method is chosen, the more data there is, the wider the sample points will be distributed and the more accurate the interpolation result will be. Now, before we do this exercise, which is based on inverse distance weighted interpolation method, let's talk about this method for a moment. Now, IDW estimates the cell value by calculating the weighted mean of the sample points in its vicinity. The closer the center of the sample point is, the greater the weight value is. The power of the value is related to the calculation of weighted distance. The power of these values is related to the calculation of weighted distance. The lower the power value, the smoother the interpolation results. The higher the power value, the more detailed the interpolation results. Right. So what are we going to do in this exercise? We're going to get a raster dataset based on the point dataset called AWS. and we will use the field temperature for interpolation. The data that we will use in this exercise is contained in the data folder and it's called rasteranalysis.udb. So let's go ahead and do this. Right, so here we have our raster analysis data source open in iDesktop, and we have opened our AWS point dataset into a new map. And to run our operation, we're going to go under the spatial analysis ribbon, and under raster analysis, we're going to say interpolation. Now here, the data source is correct. The input dataset is also correct, but we're going to change the field to temperature. And we're going to leave everything as is, and we're going to say next. Now here we are going to leave everything as default, including the power, and we're going to say finish. And there we have our interpolation result. Let's open it up, and there we have our interpolation result according to our point data set. Right, so the next logical step in our exercise is to clip our interpolation result using the China map dataset so that we can see the result onto the Chinese map. And we're going to be using map clip in order to achieve this. So let's go ahead and do this. So here we have our interpolation result, and we are going to drop the China polygon onto it. There we go. And we're going to select this, and we're going to go under map, the map ribbon, and we're going to say map clip, and we're going to say objects, and we're going to leave the settings as the same. Make sure it's union clip, and we're going to say OK. And this is our result here, and there we have our clip. Now before we move on to our next operation, it is imperative that we are able to read the information on this operation that we just carried out. So in order to know the significance of the map we just created, we're going to enable grid values. Now in order to do that, we're going to go on the analysis ribbon, and we're going to click on the little arrow next to the grid value button, which is under raster analysis. And we're going to say grid value. Now as you can see, a pop-up appears next to our cursor here, and it displays a lot of information. Now the value that we are interested in is the cell value, which is the third last value in this set of information. Now for this specific map and the operation that we just created, the cell value displays the temperature at different places on this map. For upcoming operations, this cell value is going to display something else. So that is something to keep in mind, and let's move on to our next operation. So this is our third step in our exercise, and we're going to extract some isolines that meet the conditions on the raster surface. And our fourth and last step for this exercise is going to be extracting isoregions, whereby we extract isoregions that meet the conditions on the raster surface. So let's go ahead and do these final two steps. So we have our interpolation result here that we clipped using map clip, and we're going to go under spatial analysis, and under raster analysis we're going to say surface analysis, and under surface analysis we will say extract isolines. Now here we are going to keep everything as default. We are just going to change the interval to 4, and we will say OK. And there we have our isolines, and in order to take a look at these better, we're going to drop it onto our map here. So there we have it. And the final step is to get our isoregions, and to do that we are going to go under spatial analysis, and under raster analysis we're going to go to surface analysis, and we're going to say extract isoregions. Now here we're going to select the new interpolation dataset, and we're going to say interval as 4, and we're going to say OK. So let's open this up. So there we have it. Right, so our next feature for discussion is slope. Now slope reflects the oblique degree, that is the angle between the tangent passing a point on the surface of the earth and the horizontal flat. The value of each cell represents the degree of the slope. The larger the value is, the more oblique the slope is. An application example for the slope is water and soil loss research. That means we want to see how much soil the water is taking away, and related examples. So let's see what exercise we can do on this. So our exercise is to calculate the slope value for the dataset DEM. We will make a range map for the slope result, and the red pixel slope value will be more than 30 degrees. So let's go ahead and do this. So here we have our DEM dataset open from our raster analysis data source. And we're going to go under spatial analysis, and under raster analysis we will go into surface analysis, and under surface analysis we will say slope analysis, which is under terrain calculate. So there we have our settings. We're going to leave them as default and we're going to say OK. So there's our slope result. Let's open it up. So there we have it. Right, so just like our previous operation, we are going to go under analysis, and under grid value we're going to say grid value so that we can see certain values about this operation. Now the cell value over here, as opposed to the previous operation, shows the slope value or the altitude. So that is something to keep in mind. Right, so we will now talk about aspect, meaning slope direction. An example would be paying attention to some areas in specified slope direction, such as the area which faces south. The value of each cell represents the steepest downslope direction from each cell to its neighbors. The slope direction value is calculated clockwise from due north, and the slope direction ranges from 0 to 360 degrees. So our exercise is to calculate the slope direction for the DEM dataset. We make a range map for the aspect result. So let's go ahead and do this. So here's our slope result, and we have it selected and open. And we're going to go under spatial analysis, surface analysis, and under terrain calculate we will say aspect analysis. So leaving everything as default, we're going to say OK. And there's our aspect result. Let's open it up. And there we have it. Right, so just like the previous operation, we're going to check its grid value. So analysis, grid value, and the first option. Now, the cell value that we see over here starts from the north at 0, and then it goes clockwise towards whatever the value is on a specific pixel. So these cell values are in degrees. So another thing to keep in mind. So moving swiftly on, we have our ortho image or orthographic image, which shows the variation of grid values by variation of colors, such as elevation. Now the result of an orthographic image looks like 3D data. So our exercise for this is to make an orthographic image for dataset DEM. So let's go ahead and do this. So we're going to be using our original DEM dataset, and we will go under spatial analysis, and under surface analysis we will say ortho image, which is also under terrain calculate. So ortho image. So again, leaving everything as default, we're going to say OK. And there's our result. And as you can see, it looks like a 3D image. Next, we're talking about Hillshade. This allows us to determine the illumination of each cell to enhance 3D effects. It creates a shaded relief view from a DEM dataset or a grid dataset by considering the illumination angle of the light source. So our exercise is to make a 3D Hillshade map for dataset DEM. We will overlay Hillshade result map with the original DEM dataset. Set the DEM layer's transparency as 35. So let's go ahead and do that. Right, so for this exercise we need our original DEM dataset again. And we're going to create a 3D Hillshade map here. So with this layer selected, we're going to go under spatial analysis, surface analysis, and 3D Hillshade map. We're going to add our original DEM dataset into this, and leaving everything as default, we're going to say OK. And this here is our Hillshade map. We're going to right click on this, and we're going to set the color table to, well, we're going to set a gradient of color from white to black. So there we go. So there's our 3D Hillshade map, and what we want to do is we want to drop our original DEM layer on top of this, and while our original layer is on the top, we want to change its transparency, and in order to do that we're going to go into the layer properties, and there's a transparency value, and we're going to change it to 30. There we go. And let's see if this looks better at 35. And yes, it does. So, and this is how you get an overlaid map. So these are the steps that we just did. We had our original raster map, and then we created a Hillshade map from this raster map, and then we put both of these into a single map with the original raster image being the topmost layer, and then we changed the transparency of the topmost layer to 30 or 35% in order to get our overlaid map. So that's it for today's tutorial on raster analysis. If you have any problems, please turn towards the help document